Welcome to the SAR channel, where sound and audio are demystified. There are two main ways to reduce audio file size. The first is perceptual, lossy coding, which makes files smaller by removing sounds the human ear can't easily hear, aiming to keep the audio quality nearly the same. This method combines how we perceive sound with signal processing techniques. The second is lossless coding, which also compresses the file but restores it exactly to its original form during playback. Because the restored version is identical to the original, the sound quality remains unchanged. However, lossless compression doesn't reduce file size as much as lossy methods do. In lossy perceptual coding, the exact shape of the sound wave is replaced by how it is heard by the human ear. Using a psychoacoustic model, a study of how we perceive sound, the codec encoder-decoder finds parts of the signal that can't be heard and removes them to save space. It also encodes the remaining data efficiently to avoid repeating information. These steps greatly reduce the file size, but also create quantization noise. Most of this noise can be shaped and hidden below the levels the ear can detect. This raises an important question: how much noise can be added before it becomes noticeable? Psychoacoustics helps us understand how our ears interpret sound. A perceptual coding system keeps only the information we can actually hear. Since the human ear is the listener, the codec's goal is to make the sound match what we would perceive naturally, without wasting data on inaudible details. The main goal of low bitrate coding is to reduce the amount of data needed to store or transmit sound. This data rate depends on both the sampling frequency and word length. Lowering the sampling frequency saves data, but also cuts off high-frequency sounds, as explained by the Nyquist theorem. Shortening the word length reduces data too, but it also decreases the dynamic range by about 6 decibels per bit and increases quantization noise. A better solution uses psychoacoustics, keeping the same sampling rate but adjusting the word length dynamically based on what the ear can hear. This method takes into account masking and other hearing factors to hide noise beneath the threshold of audibility. By using psychoacoustic principles, the codec can make added noise practically inaudible. Perceptual codecs analyze both the frequency and amplitude of the sound. The encoder removes unnecessary and repetitive information, reducing the data size without noticeable loss in sound quality. Even though this process is lossy, listeners usually can't tell the difference. Because humans don't perceive every detail in a recording, these codecs can deliver high-quality audio with far less data than traditional systems. Much of this efficiency comes from adaptive quantization. In standard PCM, every sound gets the same bit depth. In perceptual coding, the number of bits changes based on what is audible. Loud or important sounds receive more bits for clarity, while quiet or inaudible ones get fewer, or none at all. This flexible bit use lowers the overall bit rate, and the ratio between input and output data is called the coding gain. At the core of a perceptual codec is the bit allocation algorithm, which decides how to distribute bits across the sound spectrum. Its job is to minimize audible noise while staying within the set data limit. Perceptual coding also handles errors better than PCM. In PCM, errors cause wideband noise, but in perceptual codecs, errors are usually confined to narrow frequency bands, sounding like small bursts of low-level noise instead of clicks. These codecs can also apply targeted error correction, giving extra protection to delicate sounds like quiet piano notes while using less for louder ones. Since perceptual codecs shape the sound according to human hearing, they can also improve how audio systems reproduce music. Unlike live sound, recorded music must go through electronic playback equipment. By removing inaudible details, perceptual codecs can reduce the strain on playback systems and help them reproduce audible sounds more accurately. In essence, perceptual coding creates a more efficient and realistic representation of the sound we actually hear. Low bitrate lossy codecs whether for music or speech, aim to reduce data size while keeping quantization errors as small and inaudible as possible. Time domain codecs, like delta modulation, compress data by predicting sample values based on previous ones. These methods work on the full audio bandwidth and spread quantization noise across the entire frequency range. While the audibility of this noise depends on the signal itself, it's often not hidden or masked by it. Time domain codecs can reduce data by up to about 2.5 times, keeping quiet sounds accurate but losing more quality with louder signals. Although they achieve some compression, the bitrate often remains too high because they don't take full advantage of masking effects. Frequency domain codecs work differently. They analyze the sound by frequency instead of time and only keep parts of the signal that the ear can actually hear based on psychoacoustic models. Sounds that are too quiet or masked by louder ones are considered inaudible and left out. The codec also changes the quantization precision dynamically, allowing more noise near strong parts of the signal, knowing it will be hidden when the sound is reconstructed. This method achieves much higher data reduction, but it also makes the codec more complex. There are two main kinds of frequency domain codecs: subband and transform codecs. Subband codecs divide the sound into a few frequency bands and analyze short time segments, giving good time resolution but weaker frequency resolution. Transform codecs, on the other hand, use many more bands and analyze frequency details more precisely, providing excellent frequency resolution but poorer time resolution. Transform codecs also reduce unwanted frequencies more effectively, but introduce longer processing delays than subband codecs. In subband coding, the audio signal is divided into several frequency bands, and each band or subband is coded separately. Different numbers of bits are assigned to each subband depending on how important or audible it is. Some quantization noise is added within each subband, but when the signal is played back, that noise stays within the same subband and is usually masked by the sound present there. This means that even if the noise exists, it isn't noticeable when covered by the signal. Subbands that contain no audible sound are set to 0, saving data. The bit allocation for each subband is decided by a psychoacoustic model that analyzes what the ear can hear. This process is repeated for every new block of data, and the quantization changes dynamically, depending on how audible the sound and noise are. Different codecs may use various psychoacoustic models and bit allocation algorithms. During playback, the decoder reconstructs each subband and combines them through a synthesis filter bank to rebuild the full audio signal. A perceptual subband codec splits a short section of audio into several frequency bands using a filter bank. The encoder then applies a psychoacoustic model to calculate a masking curve that defines what parts of the sound are audible. The energy level of each subband is measured to see which ones contain audible content. Then, the average power of each subband is compared with the hearing threshold, giving the final masking level. Any subband with sounds below this level isn't coded. Similarly, tones that are hidden by louder neighboring tones or entire subbands masked by others are skipped to save bits. Bits are assigned according to a priority system. More bits go to subbands with stronger or more audible sounds, above the masking curve, while fewer bits go to quieter, less audible parts. Sounds that fall below the masking threshold can still be coded, but only with lower priority. In all cases, the quantization noise is kept below the combined masking curve so that it remains inaudible to the listener. In transform coding, the audio signal is treated as mostly stable over short time periods. To compress it efficiently, small blocks of time domain samples are converted into the frequency domain. Instead of coding the raw amplitudes, the codec encodes frequency coefficients, which are then quantized to reduce data. For playback, these coefficients are converted back into the time domain. This process mimics how the basilar membrane in the ear separates sounds by frequency. The codec uses a psychoacoustic model to decide which parts of the spectrum to keep. Quiet or masked sounds are removed, and quantization is adjusted based on what can be heard. Longer transform blocks provide better frequency resolution, more detail and tone, while shorter ones give better time resolution. Most codecs switch block lengths depending on the signal. Short blocks for fast changes or transients, and long ones for steady sounds. After conversion, each group of frequency coefficients is quantized according to the psychoacoustic model. Quantization may be uniform, non-uniform, fixed, or adaptive depending on the band. All low bitrate codecs process audio in short blocks, small enough to stay within the temporal masking range of human hearing. If a block is too long, quantization noise may be heard before the actual sound, creating a pre-echo, a faint noise that appears just before a sharp transient, like a drum hit. This happens because the noise spreads across the block's duration, while the transient is very brief. When this spread occurs over a long block, the pre-echo becomes audible. Transform codecs face this issue more often since they rely on long blocks for better frequency detail. However, shorter blocks, while reducing pre-echo, lower frequency accuracy and increase data overhead. Essentially, transform codecs trade time accuracy for frequency accuracy. Long blocks work best for steady or tonal sounds, while high spectral resolution allows the codec to identify peaks and use them for masking in bit allocation. To handle this, many transform codecs use adaptive block lengths, changing between short and long depending on the signal. Short blocks keep noise brief and masked, while variable bitrate VBR encoding can raise the bitrate slightly to reduce noise when needed. Some codecs also use temporal noise shaping, TNS, which reshapes quantization noise to follow a transient's envelope, making the noise less noticeable. Still, music often contains both steady and transient sounds at once, creating competing demands for the codec. In adaptive transform codecs, each frequency band is quantized with the same bit depth within the band, but the number of bits per band is chosen adaptively. The bit allocation algorithm decides how to distribute bits so that the signal-to-noise ratio is optimized, keeping noise masked while staying within the bit rate limit. Extra bits can be iteratively assigned where needed to maintain quality without exceeding the target data rate. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. In low bitrate codecs, an analysis filter bank is used to split the full audio range into several smaller subbands, making it easier to process and compress. During playback, a synthesis filter bank combines these subbands back into the complete audio signal. In uniform filter banks, each band is spaced evenly and the signal is shifted down to a baseband, then passed through a low-pass filter and subsampled to reduce data. Ideally, time domain filter banks would perfectly separate low and high frequencies. However, in practice, real filters have overlapping frequency bands, meaning the separation between them is not completely clean. When an audio signal is split into subbands, each subband is subsampled so that the total sampling rate stays the same. According to the sampling theorem, the sampling frequency must be at least twice the bandwidth of the signal being sampled. In practice, most filter banks aren't perfect because their transition bands are limited in width. This causes the frequency bands to overlap, and subsampling can create aliasing unwanted frequency distortion. Quadrature mirror filters solve this problem by allowing the original signal to be perfectly reconstructed from the overlapping subbands. During playback, the aliasing components cancel each other out in the frequency domain, and each subband is correctly restored to its original position in the output signal. While filter banks with evenly spaced frequency bands are commonly used, they don't match the way the human ear naturally divides sound into critical bands. To fix this, tree-structured filter banks are used, which can better align with the ear's frequency sensitivity. A polyphase filter, also called a pseudo-QMF or PQMF, creates multiple filters with equal bandwidths and specific phase relationships that make processing very efficient. It can be built as a finite impulse response filter that performs both interpolation and decimation at the same time. Polyphase filter banks provide good accuracy in both time and frequency, with strong stop band attenuation of up to 96 decibels to reduce unwanted aliasing within each band. The Modified Discrete Cosine Transform, MDCT, offers detailed frequency analysis and allows 50% overlap while maintaining critical sampling. Because of this efficiency, it is widely used in many audio codecs. Masking quantization noise in mono audio is simple because both the sound and the noise come from the same point. However, stereo and surround sound add spatial cues, making coding more complex but also more efficient at low bit rates. Coding can use similarities between channels to reduce data, but it must also respect spatial masking since our ears are highly sensitive to direction. Most masking studies are based on mono sounds, so stereo unmasking, where noise becomes audible due to poor spatial matching, can be a problem. The effect also differs between speakers and headphones. Above 2 kHz, our sense of direction depends more on how sounds are masked over time than on fine-time details. Coding errors must therefore be hidden across time, frequency, and space. If stereo channels are coded poorly, one may interfere with the other, breaking the stereo image. Dual monocoding treats each channel separately, while joint monocoding shares a total bit rate between them. Independent channel coding can cause audible noise if spatial masking isn't aligned properly. Multichannel coding must handle the delicate psychoacoustics of how both ears perceive sound. Joint stereo coding improves efficiency by using shared information between channels. Since stereo usually shares level and phase data to create a spatial image, it's more efficient to code this common information once instead of twice. Many codecs use mid-side encoding to remove redundant mono content. MS encodes a mid, some, and side difference signal rather than left and right channels, and the decoder reverses this process. This method helps avoid spatial unmasking in symmetrical channel setups. Another method, intensity stereo encoding or channel coupling, focuses on high frequencies. Since we perceive these mainly by their energy patterns, it encodes the energy envelope instead of the full waveform, making it especially useful for efficient spatial sound reproduction. In many systems, perceptual codecs are used one after another in a chain. Each codec adds its own quantization noise on top of what the previous codec already introduced. Since psychoacoustic models track masking levels rather than actual noise, this buildup can make the noise audible. Once the noise reaches that level, the codec may start using bits to encode the noise itself, leaving fewer bits for the rest of the signal and causing even more distortion elsewhere. Tandem codecs also may not align perfectly. They use different frame boundaries and timing. This can create noticeable noise, artifacts, or pre-echo. To avoid this, the process should begin with the highest quality codec, since a low-quality one will limit everything that follows. High-quality codecs with a larger margin between masking and coding noise can handle more re-encodings without much loss. To reduce degradation, the next encoder can reuse the same parameters, such as quantization, filter banks, framing, and stereo encoding, from the previous codec. Doing so allows the signal to be re-encoded almost exactly, minimizing quality loss even after several generations. Some systems can extract these parameters directly from the decoded bit stream, reconstructing the signal as if it were encoded only once. Certain codecs embed metadata inside the audio using hidden, steganographic methods. This metadata stores key encoding information, ensuring later codecs can match the original settings and avoid extra distortion. Using the same frame alignment, psychoacoustic model, and quantization keeps every stage consistent. With the correct parameters, the final encoded stream can closely match the original within filter limits. Some systems even process signals directly in the codec domain, skipping conversion to PCM and back, which helps prevent quality loss from repeated encoding and decoding. Every perceptual codec must find a balance between sound quality, bit rate, and unwanted noise. By narrowing the encoded audio's bandwidth, more bits can be used for the remaining part of the signal. Spectral Band Replication (SBR) helps achieve this by lowering the bandwidth during encoding and then expanding it again during playback. SBR mainly works at the decoder side, where it restores the high frequencies of the sound. The lower part of the spectrum is sent through the main codec, while the higher frequencies are recreated by the SBR decoder using the lower frequency data and some control information. The recreated high frequencies don't exactly match the original signal, but they sound natural enough to the ear, which is less sensitive to small differences at high frequencies. SBR can be applied to mono, stereo, or multi-channel audio. At low and medium bit rates, it can make a codec up to 30% more efficient, depending on the specific codec used. It works best when the codec already provides acceptable sound quality in a limited bandwidth. A simplified version, called low-complexity SBR, can even work without any control data. This is known as blind decoding. Traditional audio coding is judged by measurable data and technical specifications, but perceptual coding depends on how humans actually hear and perceive sound. With digital signal processing, engineers can now create systems that listen more like the human ear. Linear measurements can show some weaknesses in perceptual codecs, but they cannot fully reflect how accurate the sound feels to listeners. Unlike traditional audio systems, which behave mostly linearly, perceptual codecs are highly nonlinear, just like human hearing. Measuring how noticeable coding noise or artifacts are is complex, because psychoacoustics still struggles to find truly accurate ways to connect sound measurements with human perception. Basic tests can still reveal compression artifacts. A sine wave generator can produce tones at different frequencies, and an oscilloscope can compare compressed and uncompressed waveforms aligned to correct for codec delays. Any extra noise, distortion, or glitches can then be seen. Testing with no input signal helps reveal idle channel noise, while testing with low or high signal levels helps show noise, floor, and headroom. More advanced tools like distortion or spectrum analyzers can also be used, though interpreting their results is tricky. Traditional distortion and noise tests don't meaningfully describe how perceptual codecs sound. In theory, the best objective way to test a perceptual codec is to use an artificial ear, a model that simulates how humans hear. Such a system can detect codec flaws and measure the noise-to-mask ratio, where a positive NMR means the noise is audible. However, these tests are only as good as the artificial ear itself. Since each model is based on subjective design choices, test results vary depending on the reference used. Ideally, if a codec used a reference model that was better than its own internal hearing model, it could reach perfect performance. But in practice, testing remains somewhat subjective and limited. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. The most reliable way to evaluate a perceptual codec is through extensive listening tests with many participants. This method, when combined with proper analysis, is considered the gold standard. Listening tests should be blind, use expert listeners, and apply statistical methods to ensure the results are reliable. It's useful to link listeners' subjective impressions with objective codec parameters. This helps designers identify where audio quality can improve and how much the bitrate can be reduced without noticeably affecting fidelity. Using agreed-upon definitions for subjective terms creates a common language for listeners and provides a basis for objectively analyzing their opinions. The main goal is to connect what listeners hear with measurable data. This is challenging because correlations are not always known. Research, particularly through critical listening, is necessary to explore these connections. Even without perfect correlation, listening tests remain essential. High-quality headphones are often used to hear fine details and eliminate room acoustics or background noise. For multi-channel audio, loudspeakers are necessary, and the listening room must have good acoustics and be quiet. To get meaningful results, listening tests must be analyzed using accepted statistical methods, considering factors like the number of listeners, number of trials, and confidence intervals. Often, multiple tests from different perspectives are needed to fully evaluate a codec's performance. Several methods and standards exist for conducting listening tests, including guidelines for room acoustics. Some tests focus on determining whether a codec is perceptually transparent, meaning expert listeners cannot hear a difference between the original and encoded audio, using various test signals and music. Other tests aim to measure the coding margin, or how much the bit rate can be reduced before transparency is lost. Key factors in listening tests include the audio material, playback system quality, listening environment, listener expertise, grading scale, and data analysis methods. Music should be chosen to expose known weaknesses in a codec. Sounds with transients and complex tones in the ear's most sensitive range, 1 kHz to 5 kHz, are particularly useful. To make listening test results meaningful, they must be carefully analyzed. Statistical analysis helps interpret the results, showing how likely they reflect real differences rather than chance. Since listening tests are based on samples, larger groups of listeners give more reliable results. The key point is significance. If results are significant, they reflect true differences in listening. If not, they could be random. However, statistical methods cannot fix a poorly designed experiment. In other words, even impressive statistics cannot make flawed tests valid, so careful test design is essential. Lossless data compression works differently from perceptual lossy coding. While lossy coding removes parts of a signal that are less noticeable to the ear, lossless compression focuses only on redundant data. It creates a smaller file that can be fully restored to the original bit-for-bit signal, so the sound quality is completely unchanged. Unlike lossy coding, no information is lost. The average information in a signal over time is called entropy. Adding redundancy increases the file size, while removing redundancy reduces it. This is the basis of lossless compression. An ideal system eliminates all redundancy but leaves entropy intact. Entropy determines the minimum number of bits needed to represent a digital signal, and a dataset cannot be compressed beyond the product of its entropy and the number of elements in it. Entropy coding is a type of lossless compression commonly used in audio and video. It works by using the probability of each value in a signal to assign codes. Frequently occurring values get shorter codes, while rare values get longer codes. The decoder knows these codes and can fully reverse the process. Because nothing is lost, the compression is completely reversible and preserves all original information. Perceptual lossy coding can greatly reduce the bit rate, but it always slightly degrades the signal. Lossless compression, on the other hand, keeps the signal bit for bit accurate, though the reduction in bit rate is smaller. Every audio signal contains information. Rare or unpredictable samples carry more information, while common or repeated samples carry less. Tonal signals, like pure sine waves, have high redundancy, while noise-like signals have low redundancy. Usually, a sample's value is similar to its neighbors. Predictive coding uses previous samples to guess the next one, transmitting only the prediction error. The decoder reconstructs the original sample by adding this error to the prediction. Compression must respect the system's maximum bit rate, even for difficult-to-compress passages. A predictive coder aims to guess each sample as accurately as possible to minimize the bits needed. To do this, it shapes the signal so the prediction error has a flat spectrum. High-frequency content can limit prediction accuracy and increase bit rate, so the coder adjusts its strategy dynamically, including skipping coding if needed. Errors in transmitted data can propagate and disrupt decoding. Encoders must detect uncorrected errors and mute output to prevent audible glitches. Peak bit rate is often more critical than overall reduction, and buffers or word length adjustments can help manage peaks. Higher sampling frequencies help reduce overall and peak bit rates because upper frequency audio carries little energy. Lossless compression works especially well at high sampling rates where the top frequencies mostly contain dither or quantization noise. The bitrate reduction depends on the input word length, with lower precision signals compressing more efficiently. Each extra input bit adds roughly 1 bit to the compressed output. Unlike lossy coding, lossless compression does not use psychoacoustic principles like masking. This makes development simpler since transparency is guaranteed and subjective listening tests aren't needed. However, timing and jitter still require careful engineering. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.